All right, so today we're just going to be talking about projections and least squares. And so I'm just going to start by talking about projections. All right, so let's say that we have V, which is going to be a subspace in some Rn, okay? All right, so I'm going to draw a picture, and I'm going to draw V as if it were a plane, okay? All right, but it doesn't have to be a two-dimensional subspace. It could have been any dimensional subspace of Rn. I can't draw that many dimensions, so we're just going to settle with me drawing V as if it were two-dimensional, okay? All right. Now let's say here's the origin, and then here I'm going to draw I'm going to draw a vector now, which I'm going to call B. So this vector B that I've drawn is sticking out of the plane, meaning that this vector B is not inside the space V, okay? So it's a vector Rn, but it's not in the subspace V, okay? All right. So this vector that I'm going to draw over here, I'm going to call this vector P. So this vector P represents the projection of the vector B onto the space V. Okay. And so what's special about this projection vector? So there are two things I want to note about the projection vector. Okay. So first is that it makes a right angle here. And this vector in blue that I've drawn, the vector connecting from P to B, this vector would be the vector B minus P. Okay. So one way that you can see that is since these vectors are connected head to tail, that means that their sum has to equal vector B. And so for the sum to equal to B, this must have been B minus P. All right. So one property of the projection vector is that the difference B minus P is going to be perpendicular or orthogonal to the space V itself, okay? And since it's a vector which is orthogonal to V, another way that you can say this is that B minus P is going to be in the orthogonal complement of V. Okay, so that's one observation. Another important fact about the projection vector that I've drawn here is that among all of the vectors which lie within V, the projection vector is the one that is closest to the vector B, okay? So among all vectors in the subspace V, the projection vector P is the one that is closest to the vector B, okay? All right, so then if at any time you have a question, just type it into the chat. All right, so I'm going to go ahead and continue. All right, so we're going to talk about how to compute this projection vector. So how to compute the projection of a vector onto a subspace of Rn. Before I talk about how to do that, though, I want to go over an application of projections. But I think before that, what I can do right now is we can go over a very special case of this. Okay, so for the simple case where, let's say that our subspace V is one-dimensional, okay? So in the case where V is one-dimensional, the situation is simple enough where we can easily figure out how to compute this projection vector. So I'm going to go ahead and just work out what this special case is. So dimension of V is 1. That just means that V is a line. Okay, so here I've got a line for V. And then let's say here is some vector that lies on that line, which I'm going to call A. And then let's say that this is my vector B, okay? All right, so when we project B onto the space V, okay, so this red vector, there you go, would be the projection of B onto V. Okay. And since V is just a line, notice that vectors A and P, they're going to be multiples of each other because they lie on the same line. So what we can say right now is that the projection vector P is going to be a scalar multiple of the vector A. All right. And we can actually figure out what this scalar is by using the fact that so I talked about how when you do B minus P, this vector is going to be orthogonal to V. And in this case, if it's orthogonal to V, that means that it must have been orthogonal to the vector A, okay? And we know that for two vectors to be orthogonal to each other, that means that their dot product must be equal to 0. Okay, so what I'm going to do with that equation is I'm just going to replace P with Ka. All right, and then here, if I distribute the A into the parentheses, so we're going to get B dot A minus k times a dot a equals 0. And rearranging this equation, you can solve for k. So let's say if we move it over to here and then divide by this, you get that k is b dot a, or I'll write it as a dot b, and then over a dot with a. And then if I plug that into this formula, then we're going to get this into this equation, we're going to get this formula. So a dot product b over a dot product with a times the vector a itself. And this would represent the projection of the vector b onto the space V, okay? All right. Okay. Now, for those of you who took 2419 or 2415, then you've seen this formula before. And so this was a formula for the projection of B onto vector A. Okay. So here in 2418, we kind of see that it's not just the projection of B onto the vector A. It's really more projecting B onto the line, which is spanned by the vector A. Okay. All right. So there's a little connection to some of the other classes that you may have taken. And we're going to work out a general formula for the projection. So like for any dimension for V. But first, I'm going to talk about an application, which is least squares. All right, and again, let me know if you have any questions at some point. Yeah, I'm going to be doing some examples. Were there specific practice problems that you were interested in? Yeah, so yeah, we'll definitely do some examples with projections and whatnot, okay? All right, but first we'll talk about least squares. Okay, so in this semester, you've been studying linear systems of equations, which we know that we can express as a matrix equation as like AX equals B. And so roughly up to the first exam in this class, you were mostly dealing with the case where your system had a unique solution. And you learned how to find the unique solution by doing elimination and back substitution. Then after the first exam, up until now, you've been focused a lot on the case where you have infinitely many solutions. So you've worked a lot with like problems where you have free variables. So you would parameterize them in order to write out what your solutions were. But we also know that there's one more case, which is that your system of equations could also have no solution, okay? So This application of projections, these squares, concerns the case where our equation has no solution, all right? Okay. So what can we do if the equation has no solution? Okay, so what we can try to do is find what would come like closest to being an actual solution to this equation, okay? So we're trying to like solve this equation as best as we can by finding something that kind of comes close to being a solution, okay? Okay, so let's think about how we would do this. Okay. Now first, if we're saying that this equation has no solution, so for the equation to have no solution, that's equivalent to saying that the vector b is not in the column space of A. So this is something that I've talked about many times before in many of my previous reviews, that this equation ax equals b will have a solution if and only if b is a linear combination of the columns of A, or in other words, there is a solution if and only if it is in the column space of A. So therefore, no solution means it is not in the column space. All right, so incidentally then, if I were to draw a picture of this situation, that picture will look very much like the pictures that I drew when I was talking about projections. We have a subspace of Rn, in this case, the column space of A, and we've got a vector B, which is not inside of this space, okay? All right. Now, we talked about how among all vectors in the column space, the projection vector here is going to be the vector which comes closest to the vector B, okay? So because of that, the closest that we can expect to solving the equation ax equals b is to instead consider this equation ax equals p, okay? So this equation, it is going to have a solution. Because the projection vector p is inside the column space. Okay. And because p is the vector in the column space which is closest to the vector b, then in a certain sense, this is the best that we could hope to do in solving the original equation, okay? All right, so any solution to this equation ax equals p is called a least squares solution to the original AX equals B, okay? And so you should think of the least square solution as being the closest thing that you can find to an actual solution to this equation, okay? So it's not necessarily an actual solution if this equation had no solution, but just to being a solution as we can, okay, as we can get. All right. Now, let's say that we wanted to find the least square solution, okay? And, whoops. I'm just going to abbreviate least square solution as LSS. Okay, so the least square solution is a solution to this equation. So it looks like we would first need to find what the projection vector is. And then once we find the projection vector, we could then try to solve for x to get the least square solution. Okay. But it turns out with just a little bit of cleverness, we can actually find the least square solution without finding the projection vector. Okay? So here's how we are going to do that. All right, so the key to this is, again, using this fact here that this vector b minus p is going to be orthogonal to, in this case, it would be orthogonal to the column space of A. Okay. All right, so because it's in the, or because it's orthogonal to the column space of A, well, we learned last time how the orthogonal complement of the column space was the left null space of A. Okay. So in other words, we can say that B minus its projection will be in the null space of A transpose. And then being in the null space of A transpose would mean that A transpose times B minus P should equal 0. Okay, that's the definition of null space. Okay, so if we're looking for a solution to this equation, then what I can do is just replace P with AX. Okay. So then any least square solution is going to have to satisfy this equation now. And if I distribute the A transpose and then just rearrange a little bit, we're going to get this equation, A transpose A times X must equal A transpose B. All right. So this represents a system of equations, which I see people often refer to as the normal equations. Okay. And so any solution to the normal equations will give you a least square solution to AX equals B. Okay. All right. So if your equation ax equals b is not solvable, the best you can do then is solve the normal equations to get the least squares solution. So I'm going to do an example now, just illustrating all of these ideas. Okay. All right, so let's say that I have some points plotted in an xy plane. So let's say one point is the point 0, 1. Let's say we have the point 1, 2. And then maybe this point up here, 2, 5, okay? So let's say these are data points from some kind of study that we were doing, okay? And then just to make it a little bit easier to see, I'm gonna write down what those points were in a table. All right. So something that you often try to do in applications is, after gathering some data points, if you create a scatter plot with them, often something that you try to do is find the equation of the line that best fits your data. Okay. And so in order to find the equation of the best fit line, we can do that by using the idea of least squares. Okay. So let's see how that would work. All right, so we know that for the equation of a line, one way that you can write it out is in this slope-intercept form, y equals mx plus b. Let's see here. I think instead of using b, I'm going to use c instead, just because I often use b for, ax equals b. So just to be sure I'm not confusing, I'm just going to use c instead here. Okay. All right, so what we can do right now is plug our data points into this equation of a line. Okay, so the first data point is y is 1 and x is 0. The next data point gives me the equation 2 equals 1n plus c. And then using the last data point, we'll get the equation 5 equals 2n plus c. Okay? All right. Now, if all of my data points happen to lie on a line, then I could use the system of equations to solve for the slope and the intercept. Okay. Now, however, if your system of equations does not have a solution, so that would be the case when your points do not lie on a straight line, so that you would not be able to solve for a slope and an intercept that would fit through all three of them. In such a case, that's going to leave us a system of equations with no solution. Okay. So if we have an equation of the form ax equals b with no solution, then we know that the best thing that we can do instead is to find the least square solution. Okay. All All right. So if we want to find the least square solution, okay. So to get the least square solution, we want to take a look at the normal equations now, okay? So we're going to solve the normal equations, which were A transpose A x equals A transpose B, to get the least square solution, okay? All right, so what we'll need to do is we are going to need to compute A transpose A as well as A transpose B. So let's try to do that real quickly. So here is A transpose and times A. So if we multiply that out, we're going to get 5, 3, 3, and 3. Okay. We also need to do A transpose B. Okay, so here's A transpose, and then B was 1, 2, 5. So if we multiply that out, we're going to get 12 and 8. Okay. Okay, so then the normal equations are going to be 5, 3, 3, 3 times vector x equals A trans B. And so now we can solve for x to get the least square solution, all right? Now what I'm going to do in this problem is to solve for x. You can just do the usual elimination, but what I'm going to do is I'm going to just use this formula for the inverse of a 2 by 2 matrix. Okay. So if we multiply both sides on the left by the inverse, then we would ultimately get x is the inverse of 5, 3, 3, 3 times 12, 8. All right, so using the formula that we have now, the inverse is 1 over AD minus BC. So 15 minus 9 will be 6. And then it's going to be DA negative B negative C. All right. And now I'm just going to finish multiplying everything out. So we're going to get 36 minus 24, which would be 12. And then negative 36 plus 40, which is 4. All right, so I'm going to multiply the 1/6 inside. So we're going to get a final answer of 2 and 2/3. Okay. So this is our least squares solution to the original equation that we had. All right. Now remember that the components of x represented the slope and the intercept of the equation of a line. So what this least squares solution is giving us here is it's giving us the slope and the intercept for the equation for the line that would best fit our data points. So if I wanted to write out the equation now, so I set it up to be y equals mx plus c. There is no line that passes through our data points, but from the least square solution, using 2 for the slope and using 2/3 for the intercept, this would be the equation of the line that would best fit our data, okay? Okay, so any questions about that example? All right. So then I will yeah, so the data points are used to come up with the AX equals B equation. And then from there, you will then create the normal equations from that to get the least square solution, okay? Okay. All right, so I'm going to now consider a similar question, and I'm not going to work this example entirely out, but I'm just going to kind of quickly set it up, okay? So it'll be similar. Let's just say we have some collection of data points. All right, now this time, let's say instead of wanting to find the line that will best fit through these data points, let's say instead we want to find the parabola that would best fit these data points, okay? So it's actually not that different from what we did before. Now, one thing that would change though is since we're trying to find the best parabola, then instead of using y equals mx plus c, as I did before, I'd want to use the equation of a parabola, which would be a quadratic equation instead. So let's see here. Okay, so, well, maybe not p. Okay, so I will write the equation as rx squared plus sx plus t, okay? All right. So this is a generic quadratic equation. It would represent sort of a generic formula for a parabola. Whoa, okay. So what we can do is plug all of our data points into this equation. So for instance, plugging in 1 for y and 0 for x, and then plug in 0 for y and 1 for x. Okay. So doing this is going to give us a system of equations that we could use to try to solve for r, s, and t. Oh, I see, I was confused. So the next data point, y is -1 and x is 2. And then the next one, y is 1, but x is now 3. So now it's going to be 9r plus 3s plus t. And finally, for the last data point, y is 3, and x is 4, so that'll be 16r plus 4s plus t. All right. So just as before, the data points will then give you a linear system of equations. Now, if all of your points happen to lie on a parabola, then this system of equations would have a solution. But if your data points do not lie on a parabola, then this system of equations will not have a solution. In which case, what you could do is find the least squares solution. And whatever the solutions are that you find for the least squares solution, you would then use that to write out the equation of the parabola that would best fit your data points, okay? All right. So the procedure would be the same. Compute H transpose A, compute H transpose B, and then you'd have these normal equations that you'd be trying to solve, all right? All right, but I don't want to spend any more time on that. So I'm just going to leave the example right here. Okay. So any questions about this before I go on to some more topics? All right. Now, something that I want to note is in the first example that I did, so to solve for the normal equations, what I did was I found the inverse of H transpose A. And then once I found its inverse, I got the least squares solution to be A transpose A inverse times A transpose B, okay? So a couple of things to note is first, because H transpose A was invertible, you would find a unique least squares solution. Okay. But it won't always be the case that H transpose A is invertible. So if the H transpose A was not invertible, then you would actually have infinitely many least squares solutions. Okay. So I think it's maybe good to know when would A transpose A be invertible. So I wanted to just give an answer to that question. So it turns out, I'm not going to prove it, but I'll state it. A transpose A is invertible if and only if the columns of the matrix A are linearly independent, or if you want, if and only if A has a full column rank, okay? Meaning it has a pivot in every column. All right. All right. So now I want to return back to projections and talk about how would we find the projection of a vector onto a given space, okay? Okay. So we can actually use what we talked about with least squares to now compute projections, all right? So here's the idea for that. So let's just recall just now how we talked about the least square solution is, so first it's the solution to the equation ax equals p. But after a little bit of cleverness, we figured out it was also the solution to the normal equations. So what we can actually do is we can compute the projection vector by first solving the normal equations to get the least square solution. Then once we have the least square solution, if we just multiply it by the matrix A, then that should give us the projection vector, okay? Now, one thing that I want to emphasize right now is, okay, so I'm going to scroll up real quickly to when I first started talking about least squares. Okay. So in the context of least squares, the projection vector that we ended up solving for just now would have been the projection of the vector B onto the column space of the matrix A. Okay. So I'm just going to note that right now that this procedure solves for P, where P was the projection of B onto the column space of A. Okay. So if we go back to the original picture that I had at the very beginning, so I had a generic subspace V of Rn and a vector B that was sticking out of it. And what we were originally wondering was, okay, how would we compute the projection of B onto the subspace V? All right. So in this general situation where we have a subspace V, it's not necessarily the column space of some matrix A. Well, what we can do is this. First, we can find a basis of the subspace V. Once we find a basis for V, we can take those basis vectors and put them into a matrix. We'll put them into a matrix A as columns. Okay. Then in doing this, we would have created a matrix A whose column space is the space V itself. Okay. And then we could use this procedure to find the projection of B onto the column space of A. And then since the column space of A was equal to V, that would have given us the projection of B onto V, okay? All right, now, one other thing about this procedure is if you use a basis for the space V, then the columns of A would be linearly independent because they formed a basis. So therefore, you could get the least square solution from this formula. The columns of A are independent, so A transpose A would be invertible. So then multiplying this by A would give us the projection of the vector B onto the space V. And at this point, I'm going to introduce some notation for that. So this would be the notation that I now start using for projection of B onto the space V, okay? And we have this formula for it, where the matrix A has as its columns a basis for the space V, all right? Okay, now this part over here, all right, so this part would be, we'll call this the matrix. Well, I'll call it the projection matrix. For projecting onto V. All right, so you can think of over here, so PV would be notation for the projection matrix onto V, and then that matrix times the vector B gives us the projection of B onto V, okay? All right. So I'm gonna do some examples of finding projections of a vector onto a subspace. Oh, geez. Okay, so let's say in this example, V is the plane in R3 given by the following equation. And what we want to do now is find the projection of the vector 1, 0, -1 onto the plane V, okay? All right. Now, in order to find the projection of B onto V, so I'll use the procedure that was illustrated just now. So what we first want to do is find a basis for V. So that's our first step. All right, and so to do that, we actually talked about how to do this in the last review, right? You asked me a question about that. So what we can do is use y and z as our free variables. So I'm going to assign a parameter to each of them. Then I'll solve for x. So it would be s plus 2t in this case. And then if I were to write this as a linear combination using s and t as the coefficients, we'd get the vector 1, 1, 0 and 2, 0, 1 there. And then these two vectors would give me a basis for the plane V, okay? All right, great. Now that we have a basis for V, we're going to put them into a matrix A as columns. And then now that we have this matrix A, we can compute the projection of vector B onto the plane V as being equal to all of this, okay? So now we just have to do a good deal of computation over here to get the projection vector, okay? All right, so let's start by computing A transpose A. And you know how you go about computing this is kind of up to you, the way that you choose to multiply it. Here's what I'm going to do. I'm going to start by computing A transpose A. So if I multiply this out, it's going to be 2, 2, 2, and 5. And what I'm going to do is I'm going to go ahead and get the inverse of A transpose A. And then, so to do that, I'm going to use the same formula for a 2 by 2 inverse that I did earlier. So the formula was 1 over AD minus BC. Then it was D, A, negative B, negative, whoops, and then negative C. Okay? Okay, so now we have A transpose A inverse. So now what I want to do is I'm going to go ahead and I'm going to choose to compute the projection matrix first. So PV is A times A transpose A inverse A transpose. And I'm just going to plug everything into this now. So here's A. Here was the inverse of A transpose. And finally, here is A transpose. And I'm just going to multiply all of this out now, okay? All right, let's see. So I'll start by multiplying the two of these together. So 5 minus 4 is 1. 5 should be minus 2. Negative 2 plus 4 is 2. Negative 2 and 2. All right. And then finally, just multiplying these two together. Okay, so let's see here. Be 5, 1, 2, 1, 5, negative 2, and then 2, negative 2, 2, okay? All right, so after all that computation, that would have been the projection matrix. And then finally, the projection matrix times vector B would give us the projection of B onto the plane V. Okay, so there's that. And then times vector B. And B in the problem was a 1, 0, negative 1. So I'm just going to go ahead and finish up this computation. It's going to be 3, 3, 0. Okay. And then if you wanted to, I guess you could multiply the 1/6 then, so it would be 1/2, 1/2, and 0 in the end. Okay. All right. So next, let's go back to the. Oh, well, okay. So first, maybe any questions about any of that? Yes, that is correct. Okay. All right, so now I'm going to do another example. So give me a couple of seconds. My screen is slightly frozen right now. So you've probably seen in my last couple of reviews that I do have this occasional issue where when I'm switching from e-learning to OneNote, my computer often freezes a little bit. So we'll give it a couple of seconds, and once it unfreezes, then I'll start the next example. All right, great. All right, so for the next example, I want to come back to what we just did. Okay, so we found a projection of B onto the plane V. So now, as another example, I want to find projection of B, but onto the orthogonal complement, of the plane V. Okay? All right, so I'm gonna kind of follow the same procedure for all of this. First, the orthogonal complement of V, all right? Well, so the plane V was the solutions to this equation. So in other words, we can say that V was the null space of the matrix 1, -1, -2. Okay. Since V was the set of all solutions to the equation x minus y minus 2z equals 0. And that equation is the same as this equation here. Right. So if V was the null space of this matrix, then that means that the orthogonal complement of V would have been the row space of this matrix instead, because we talked about how null space and row space are orthogonal complements. And in this case, since it's just one row, then this one vector itself would be a basis for the orthogonal complement of V, okay? So now that we have a basis for the orthogonal complement, so we form a matrix A by using it as, well, it would only be one column, okay? All right. And then we will just go through this whole process again to get the projection vector, all right? So I'm just going to just write out this whole formula for it. So it's A, Okay, then it's going to be times the inverse of A transpose times A, and then times A transpose, and then times vector b, which was 1, 0, negative 1 from the problem, okay? Okay, so let's see what happens when we do all of this computation. So I think this time what I'll do, let's start by computing A transpose times B. So that's just going to be 1 plus 0 plus 2. So A transpose B is 3. Okay, so next, if I compute, I'm going to compute the A transpose A inside the parentheses. That's going to be 1 plus 1 plus 2. That'll be, sorry, plus 4, which is going to be 6. Okay. All right, so then we have 3. Now, this is 6 to a power of negative 1. So that means I could move it into the denominator. So I'm going to have 3 over 6. And then still times the vector A. Okay. So that would be 1/2. And then if I multiply the 1/2 inside, I could write it like this. And that would be it. That would be the projection of B, onto the orthogonal complement of V, okay? All right, any questions about that? Okay, so yeah, similar to the previous example, it was just a lot easier because my matrix A was only a matrix with one column in it, okay? All right, now something that I think is kind of interesting to note is, if you remember towards the beginning of this review, I covered the case where if you are projecting onto a one-dimensional space, so I said, I derived a formula for it where I said, take a vector A that lies along that line, and what we found was that the projection of a vector B onto this line V, so the formula that we derived was A dot B over A dot A, and then times the vector A. And I want to note that we actually did the same thing just now over here. So actually, if we take a closer look at how this problem worked, so first, the orthogonal complement of V was one-dimensional. It was just spanned by this one vector. So we can treat this one vector as having been the vector A that is in this picture here. And then notice that when we did A transpose times B, that was actually the same as vector A dot product with vector B. And this would have been the same as vector A dot product with itself in the denominator because of the -1 exponent. And then that was all times the vector A. Okay. So then incidentally, the formula that we derived agrees with the formula that we got earlier for the special one-dimensional case. So that's kind of good to see, right? All right. Now, I know I'm out of time, but I'm just going to say a couple more things. Oops. All right. So here I'm just going to draw that picture that I've been drawing all this time. Got a space B, vector B, and here the projection of B onto V. And then, of course, we always had this vector up here, which was vector B minus its projection. And this vector makes a right angle with vector V, or sorry, the subspace V. Okay, so well, I'm going to add something now to this picture, which is I'm going to now add in the orthogonal complement of V. So in this picture, since V was drawn as a plane, its orthogonal complement would have been a line that was orthogonal to it. Okay, so this line passing through the origin here would be, I guess, a visual representation of the orthogonal complement of V. And so what I want to observe is that this vector here, so if I just like redraw that vector at the origin, then here you can kind of see how this vector is actually the projection of B onto the orthogonal complement of V. Okay, because it's kind of the same similar picture. Where if I drop a perpendicular down from B onto the orthogonal complement, then like you can see that this vector that we have here would have been the projection of B onto the orthogonal complement of V. Okay. So then from this, we get this kind of formula that the projection of vector B onto the orthogonal complement of a subspace V would equal B minus its projection onto the original V. And if I factor out a B from both terms on the right-hand side, so what we'd have remaining after factoring out the B is an identity, and then minus PV. So then here, one thing that we note is that the projection matrix onto the orthogonal complement, you can compute it as being the identity matrix minus the projection onto V. So that's one thing that's kind of interesting to note, and that it could be useful. Okay, so one way that we could have taken advantage of all of this just now was actually in the previous example. But I guess I'll just kind of write it out here because I don't want to be scrolling around. So how can we use in some of our problems? Well, what it says is that we can compute the projection of a vector onto an orthogonal complement by just doing this subtraction over here. So in the last example, after we figured out the projection of B onto V, we actually could have found the projection onto the orthogonal complement by simply doing this difference over here. And in fact, we can just confirm that real quickly. So if I did, in the example, vector B minus its projection onto V, so B was 1, 0, negative 1. We're subtracting its projection onto V. Notice that gives us 1/2, negative 1/2, and negative 1, which is the same thing that we got over here, computing the projection onto the orthogonal complement, but using slightly more involved procedure to get it, okay? And so that's one thing to note is you can compute projection onto your orthogonal complement by doing this property. Another thing that's interesting to note is that we also could have we also can compute projection of B onto V as being equal to B minus its projection onto the orthogonal complement, okay? So that's just kind of like rearranging this equation, okay? So how could we have used this in our previous example? Well, notice that in this example here that it was much easier to find the projection of B onto the orthogonal complement of V because the orthogonal complement was one-dimensional. So what we could have done is, after computing the projection of B onto the orthogonal complement, we could have said, okay, let's take B minus its projection onto the orthogonal complement. And then that would have given us the projection of B onto V over here. Okay? All right. Oh, I did not notice I had so many people here. All right. So I'm almost done. I just want to say 2 more things, all right? Okay. So yeah, the last thing I want to say is I'm not going to work out this example, but I'm just going to talk a little bit about it. But for this example, let's say we wanted to find the projection of some vector B onto the span of some vectors, which I'm just going to create right now. Yeah, so I always record these review sessions and I upload them to our YouTube channel after that. And yes, I actually did send out notes from a previous semester for this class. I suppose I can send all of that out again in case you don't have it, all right? All right. Let's see here. Okay, so I'm just going to talk about this example, but that will be it. Okay. So in order to do this problem, there's a couple different ways that we can do it. So I just want to talk a little bit about that. So here's what we can do. What we could do is first find a basis for the span of these four vectors. Now, note that these vectors, they're not necessarily linearly independent. We don't know if that's the case or not. So what we could do is put them into a matrix first as columns. And then what we can do is row reduce and find where the pivots are at. And remember that where the pivots are at, that will tell you which of these vectors would actually form a basis for their span. And so in this example, you can kind of confirm, but in this example, you would have gotten pivots in the first, second, and fourth columns is what would have happened. Excuse me. Right, so that means you could remove the third column and just take the first, second, and fourth columns. You can make that your matrix A, and then you can use that giant formula that we had from earlier to get the projection. All right. Now, something else that you can do though is, in this example, when you compute H transpose A, it's going to be a 3x3 matrix. So for a 3x3 matrix, it is a little bit harder to find its inverse. So you can compute the projection vector by, or like without computing the inverse of A transpose A. So how would we do that? Well, what you could do is set up the normal equations and solve the normal equations for the least squares solution. And in solving this equation, you could solve it by doing elimination and back substitution. And then once you solve for the least squares solution by doing that, then you can compute the projection vector as being A times the least squares solution. Okay. So this would be a way that you can find the projection vector without computing the inverse of A transpose A. And then for that matter, there's another way that you could have approached the problem, which is you could have just used this as the matrix A to start with. So you didn't have to first find the pivot columns. So you actually could have just worked with this right away for the matrix A. Get the least square solution from the known equations. And then get the projection vector as being A times X. So actually, you could have just done this and that also would have worked. One thing to note, though, is that here, because the columns of A were not linearly independent, you would end up finding infinitely many least squares solutions. But you can just take any one of those least square solutions and multiply it with A, and that would have given you the projection vector. Okay? So for this problem, there were quite a few ways that you could have gone about it. And I just want to mention the different ways you could have done it. You can kind of pick whatever you prefer and go with it, right? All right.